G'day guys, Mr. Bennett here. Now today we're going to be looking at lasers and how they actually work, and it incorporates a lot of the theory behind looking at the atom itself and the transfer of energy and energy levels. So laser stands for light amplification by stimulated emission radiation. Alright, so that's the acronym for laser. Now in this process, right, the one that we need to better talk about is in fact the helium neon laser. So what we have in our laser beam is, or the red one that we use in the lab, we have helium and neon. Right? So what you find is the first excited state for helium is about the same as the third excited state for, well, the second excited state for neon. Alright, so what happens normally is you will have a photon of energy that will come down that will excite an electron, and that electron will go up to the first excited state. And then what will happen normally is that will only stay there for a split second, and then it will fall down. Okay, that's what generally will happen. In this case, what can actually happen, because you've got helium and neon gas in the actual laser chamber, what can happen is that rather than falling down, as it falls down, it can hit a neon sample, right, a neon atom, and it can actually transfer all of its energy to the neon. And so therefore what's going to happen here is you're going to have a whole heap of neon electrons that are actually in the second excited state of neon. Alright, so that's what's going to happen. That process, rather than it falling down, where it transfers its energy over here, is a really important part of how this laser beam works. Alright, so obviously we stimulate that by getting our electrons into the excited state. Alright, and then what happens here is we have two terms. Alright, so in here we have a thing called a metastable state. And what that means is a metastable state is when the electrons are going to stay there for longer than normal. Does that make sense? Longer than normal. So instead of being a nanosecond, it might be 100 nanoseconds. Alright, so then what's going to happen is, we'll talk about the stimulated emission as well in a second. But what normally happens is these electrons will spontaneously they'll emit back to the ground state. That's what normally happens. Okay. Now, when we have this state here, we have a thing called a population inversion, because the tendency of what we want to have here is electrons will be in the ground state, but because we have more electrons in the excited state, we call that a population inversion. We have a metastable state because they're going to stay there for a little bit longer than what we normally would expect. Now, the next part of this process is really important. If we use photons with a certain amount of energy, right, so if we have our electrons which are up in this excited state here, so we've got all our electrons sitting up in our metastable state, but we've got our population inversion. If I introduce a photon or of light, then what we'll do, it will cause that electron there to go back down there. Right? And we know when that happens, we emit a photon. So what actually happens here is one photon becomes two photons. And they'll be identical in terms of phase, and they'll be identical in terms of wavelength. They'll have exactly the same energy. Now, you could imagine those two photons would then do the same thing and go hit another atom, and therefore it will stimulate that process. So 2 becomes 4, becomes 6, becomes 8, becomes 16, and so on. So that will happen instantly. Now we'll see it as instant because these things are travelling at the speed of light. So if you're thinking about travelling at the speed of light and how small that space is between the atoms in the gas, then you can imagine that there'll be trillions of these things happening in no time. Alright, so when we turn the laser beam on, it just seems instantly actually happening there. Alright, so population inversion, and then what we have over here is a term called stimulated emission. Now, the difference between a spontaneous emission and a stimulated emission is this one is caused directly by the introduction of the photon, okay, where spontaneous emission will actually naturally fall down and actually emit a photon, but it only emits one photon, so that's the key there. Right, now we need to understand what the parts of the laser beam are that actually allow it to work properly. So the first thing in the laser beam is we have a pump. Alright, so we have a pump which is an electrical current. So the electrical current is something that will actually produce electrons. That's really important that we actually do that. We have an active medium. Alright, so our active medium is in fact our helium and neon gas. Right, so that's our medium, and then we have a cavity with mirrors, right, and I'll draw what that might look like for you. So basically, essentially, we've got a tube, nice straight line there. In here, we have a partially curved mirror, right, and over here we have another partially curved mirror, but this one here. Alright, so that's actually a mirror, and this one here is a partial mirror. Excuse my writing. So what's going to happen here, we're going to have a whole heap of little photons buzzing around with the same amount of energy, and what's going to happen is they will line up to be going the same direction, and then what we'll have is, once we have enough energy, because this is only a partial mirror, you'll get a beam of light that goes through that partial mirror. Alright, so the idea of the mirrors is to allow the photons to bounce back and forth until they have enough energy to go through the partial mirror. And obviously, while it's in the tube, we're actually stimulating more photons all the time by our stimulated emission process. So once it gets to that critical mass, critical energy, then you get a very, very high directional beam of light. Okay, so remembering all of these particular photons are going to be bouncing back and forth in that mirror cavity. Alright, so they basically have the same wavelength and have the same phase. Alright, so that's what's really important about lasers. Alright, so our mirror cavity is an important part of that process. Now, obviously the use of lasers is immense, okay, from obviously we use them for surveying, we use them for cosmetics, we use them in industry to cut steel, right, so there's different types of lasers. We've obviously seen the LADS example where we do that. There are so many examples where we use lasers, even to the basic thing where in a supermarket we use a laser beam to scan a barcode. Right, so they are just an amazing invention of the 21st century. So and obviously the key thing there is we need to make sure that when you're using a laser beam that you need to protect your eyes, right? Because they're so intense source of light, then they can be certainly amazing. Now I'm going to show a video just on lasers, which I think you'll find quite interesting. I'll give you a little bit more information about them, but certainly in terms of the application and use of lasers, it will be certainly fantastic for you to watch. Alright, so we'll leave that here in terms of that. So you'll need to be able to describe these processes here, right? From the idea of the helium, transferring its energy to the neon to have electrons in that populated inverted state and where it's metastable, and then the concept of the stimulated emission, which is the important bit that you need to be able to describe. Okay, I'll talk to you in class.